Okay, so the next part that we have here is, so it says that we observe that tables are using the same data and employing the same formula for the calculation of the mean, but the results obtained are different. And we showed that the results were actually different, 62 and 59.3. Can you think why this is so and which one is more accurate? Of course, the first one is of course as accurate as you can get, and the second one is just some sort of approximation to the actual value. So the difference in the two values is because of the midpoint assumption in table, in basically in the second way of, so here we got the class mark, which was the midpoint of these two, the lower limit of the class interval and the upper limit of the class interval. And so basically because of this assumption, then of course the result is going to be different. Now the difference in the two values is because of the midpoint assumption, 59.3 being the exact mean, while 62 is an approximate mean. Yes, of course 62 is the approximate, and I'm sorry, I said that wrong. 62 is the approximate mean and 59.3 is the exact mean. So then based on that, the calculation that I did here is actually not right. Meaning that the difference between these two numbers is 2.7. The difference is the same. If you calculate basically what is basically 59.3 times x% is equal to 2.7, you will get x divided by 100 is equal to 2.7 divided by 59.3, and then divide basically multiply by 100, you get x is equal to 270 by 590, which is basically 270 divided by 590, which is around 0.46% different from the actual value, not 4%, but 0.4% from the actual value. So that is that. Now sometimes when the numerical values of x of I and f of I are large, finding the product of x of I and f of I becomes tedious and time consuming. So for such situations, let's think of a method of reducing these calculations. And this is basically where we are getting into making the table a little bit simpler, and then based on that we will basically derive some formulas. Now over here you saw that when we wanted to calculate f of I times x of I, we had to calculate, well, f of I times x of I. And in such cases, for example, suppose that this is still not that difficult, but suppose that you have a bunch of such numbers and you want to calculate basically, for example, all of these numbers by these numbers, and suppose that these numbers are all large, basically large numbers and basically multiplying them, well, of course, takes a lot of time. So then in such cases, what you need to do is that if it's possible, you can simplify your calculation in some way. For example, sometimes if you have to, sometimes, for example, when you want to you know that you have to calculate all of these numbers in this column by the respective values in the other column, and of course if there is for example, a common factor in these numbers that you can take out, if there is a common factor over here or over here that you can take out, you will take out those common factors, and both of the numbers and both of the columns become considerably smaller numbers. And then you multiply the smaller numbers, and then once you've done the calculation, and then you multiply back the factor that you took out. Meaning that, for example, if you have suppose that you want to calculate 65 times, for example, 105, for example, 4 zeros, right? So what you can do, so of course you can write this calculation as 65 times 105, and then once you do this part of the calculation, you can multiply everything by a factor of 10,000. And suppose that this factor of 10,000 is common between all the numbers that, for example, you could find in the class mark. So then you take this factor of 10,000 out, and then your class mark becomes all of these very small numbers. You can calculate them, you can multiply them by the f of I, and then in the end, in the formula, you put this in your formula, for example, whatever you calculate times a factor of 10,000, and then that gives you, and then you have to basically multiply your factor of 10,000 only once in the end of the calculation. So that's how it works. So what that means is that how to solve this problem, what you can do is that we can do nothing with the f of i's, but we can change each x of I to a smaller number so that our calculations become easy. So it seems that with the f of i's, for whatever reason, we cannot do anything. I don't know the reason, but that's, I suppose, is the case. And based on what I've seen, I know that, of course, with x of I, you can actually do that exact sort of thing. So now how do we do this? So what about subtracting a fixed number from each of from these x of i's? Subtracting a fixed number. So the first step is to choose one among the x of i's as the assumed mean, and then denote it by A. Okay, so what they do, basically you have to pick one of these in order to make this x of i's basically smaller. What you can do, you can basically pick one of these x of i's as your assumed mean, as your assumed mean, and then take that, basically subtract that assumed mean from every one of your basically x of i's. Okay. Now you in just a few seconds, all of this will make sense to you. So for example, what that means is that I could take, for example, any one of these, doesn't really matter, but it had better be somewhere in the middle of your in the middle of your numbers, meaning that then when you subtract the number from itself you will get a 0 over here. You will get some negative numbers over here and some and you will get some positive numbers over here. So let's try this then. Let's try this and see how it works out. So So also to further reduce our calculation work, we may take A to be that x of I which lies in the center of x1, x2 all the way up to x of n. So now let's do this part. So we can choose, for example, A is equal to 47.5. So for example, you can take this number as A, and that is your assumed mean, okay? And you will see in just a second how you will do this. It actually makes your table basically considerably simpler and easier. So you pick some number which lies somewhere between your x of i's, and you take that as your assumed mean. And so you can take basically A as 47.5, or you can take it as 62.5, but it's better if it's somewhere in the middle of all of the values that you have, because then all the numbers above that number will benefit from that number, and all the numbers below that number will also benefit from that number. Otherwise, if it's kind of unbalanced, then some numbers will benefit, some numbers will not really benefit. Now, if I choose A to be 47.5, so that's basically what I will do. And the next step is to find the difference d of I between A and each of the x of i's that I have over here, which is the deviation of A from each x of I that I have. So what I'm going to do, I'm going to erase all of this. Oh, sorry. I'm going to erase all of this and take this as A, and then I'm going to add a column over here, and here I will calculate the deviation of basically the deviation of my assumed mean from each of these x of i's. So that's going to be A minus x of I. A minus x of I, or probably x of I minus A, sorry. X of I minus A. So x of I minus A. And I can call this d of I, which most probably stands for difference or something, or deviation, I'm sorry. So, and I can call this also as x of I minus 47.5. I can write all of these over here. That's basically the same thing. Now what that means is that in this column I will write all of my x of i's, which are all of these values, and subtract from that 47.5. So then if I write, for example, so let me note down these values somewhere over here because I might need them. So 59.3 was the actual mean, and 62 was approximation. Okay, now if I need to do some calculations here. So what I'm going to do now, I'm going to basically write, for example, 17.5 minus, for example, 47.5. So 47.5, 17.5, 0, 0, and negative 30. That would be negative 30. Now, for example, 47.5 minus 32.5. 32.5. That's 0, 5, that's negative 15. So you see that these are also multiples of 15, these numbers. 47.5 minus 47.5 is 0. Over here, 62.5 minus 47.5. 62.5 minus 47.5 is equal to 0, and then you have 5 over here, and then you have 5 minus 4 is equal to 1, so that's a 15. So you see these are all multiples of 15. Then 77.5 minus 47.5 is equal to 30. 92.5 minus 47.5, 0, 12, so that's a 5, and that's a 45. So 45 times 15 times 3 is equal to 45. 15 times 2 is equal to 30. 15 times 1 is equal to 15. 15 times 0 is equal to 0. 15 times negative 1 is negative 15. 15 times negative 2 is negative 30. Well, of course, if you think about it, statistics, if you really get into it, it's also, well, kind of fun, and of course these concepts are very, very important, because these days basically there is augmented reality, there is artificial intelligence, there is machine learning, there is machine deep learning, there is all kinds of machine learning, and of course if you don't understand statistics, of course machine learning you will not be able to learn that. So it's absolutely essential that you understand that statistics. Yeah, then of course there is no way around it. But basically, when you understand the concepts through a couple of examples, then there is nothing really complicated about it. It's just a bunch of simple formulas. Okay, so 17.5. Okay, so now the third step to do here is to multiply the difference by f of I. So over here, what we calculated is the deviation of basically each x of I, the deviation of each x of I from the assumed mean. So that means that the deviation of this x of I from the assumed mean was negative 30. The deviation of this one from the assumed mean was negative 15, and so on and so forth. Now, is to find the product of d of I with the corresponding f of I, to take the sum of all the f of i's d of i's. The calculation is shown here. So, I don't understand why I'm supposed to do this. Okay, so now let's do the rest of this. So now what you want to do, of course, again, all of this will make sense to you in just a few moments. So I calculated basically x of I minus a, and or x of I minus 47.5, which I call d of I. Now, what I also need to find out is basically, now instead of x of I, you can kind of think that instead of x of I have d of I, which is, well, much smaller and much more straightforward than x of I. So now if I somehow see the formula that we had for x bar, we said that it's equal to basically sigma f of I times x of I as I goes from 1 to n over sigma f of I as I goes from 1 to n, right? Now if now basically I need to somehow get from this formula to basically, instead of x of I, somehow I need to use d of I in my formula. Now the way that you can do it is, of course, is not very easy to, I mean, probably you would not see it right now, but if I write d of I, f of I times d of I, meaning that, for example, the same as what we did over here, I calculate f of I times f of I times x of I. Instead of that, I write f of I times d of I. And that would be, for example, so this is d of I times f of I. So that means that I have to multiply these numbers by these numbers, which is much easier than multiplying these numbers by these numbers. You see, all of these numbers are all over the place, jumping here and there. It's not easy to calculate. But for example, 2 times negative 30 is negative 60, very easy to calculate. 3 times negative 15 is negative 45, very easy to calculate. That would be simply 0. 6 times 15 is equal to 90. 6 times 30 is equal to 180. And 6 times 45 is equal to 240. 240 plus 30 is equal to 270, right? And over here, if I calculate sigma f of I d of I, that would give me, of course, as I goes from 1 to n, that would give me basically 90 plus 180 is equal to 270. 270 plus 270 is equal to 400 and 140, and then can subtract from that 105. So then you have 540 minus 105. You would get what? This is 5, this is 3, and 435. 435, right? And now if I want to calculate the mean of these deviations, I could calculate it as so this is sigma f of I times d of I. So if I want to find the mean of these deviations, I would have to divide that basically by sigma f of I, of course. So if I write sigma f of I d of I as I goes from 1 to n, and divide that by sigma f of I as I goes from 1 to n, that would be basically d bar, right? I can call it d bar, for example, the deviation, the mean deviation, for example, or something like that, or the mean of deviations, for example. Now this is of course not x bar, but it is d bar, and as it is, it's good for nothing, right? So now if we somehow if we can somehow find some sort of relationship between d bar and x bar, maybe we can use it as a formula, and then in that formula, instead of x of I would have d of I, and that would make all of the calculation much easier. So now let's see what we can do do over here. So the mean of deviation, we said that we called it d bar, and we called it, and that's equal to sigma f of I times d of I, as I goes from, for example, 1 to n, and I'm not going to write these anymore. So you know basically that these are basically their I is equal to 1 to n is basically implied whenever I write sigma f of I d of I or sigma f of I. So when we were calculating d of I, we wrote it as, we defined it as x of I minus a. So in this formula, I can write, instead of basically d of I can write x of I minus a. So I can write here sigma f of I times basically x of I minus a. X of I minus a, and divide that by sigma f of I. Divide that by sigma f of I. That is equal to d bar. Now, one thing that you can do with the sigma notation, which you might not be familiar with, the first time I did this, I had to go through a whole lot of calculation to prove to myself that you can actually do this using the sigma notation, meaning that you can write this as sigma f of I times x of I divided by sigma f of I minus, and this negative sign comes from here, and then again you can write sigma f of I times a over sigma f of I. You can actually do this using the sigma notation. It does work, but of course you cannot basically assume based on using normal algebra that, okay, so since I have the sigma of this and the negative sign, then I can basically separate them this way. No, of course, the sigma notation means that you have all of these f of I times x of I minus a all added together. So you have to basically expand it, and if you need to, prove it to yourself that this actually works. And anyway, long story short, if you try this with simpler things, for example, A, B, C, and D, and things like that, it will work for you, and you can prove to yourself that you can rewrite this expression, the sigma expression, as this expression down here, okay? But I don't want to go through that anymore. It's a lot of work and unnecessary for me. You can do it for yourself, meaning that you can write, for example, I don't know, for example, sigma a times, for example, b minus c, and then divided by, for example, sigma, for example, a, and and you will see that it is actually equal to write this as, you will see that it's actually equal to possible to write it as sigma a times b over sigma a minus basically sigma 8 times c over sigma a. That you can always do. Of course, there could be some limitations on these numbers, but I suppose you can take these as all real numbers. I would think so. So anyway, this does work, okay? Although at first sight you might say that it might not work, or it might seem weird to you. And you know that sigma f of I x of I over sigma f of I, we had this over here, and that's equal to x bar, right? So this is of course d bar, and this is of course d bar, and so you can write d bar is equal to x bar minus sigma f of I times a over sigma f of I. And of course, in sigma notation, one more thing that you can do, since this a is being multiplied by each term, meaning that when you write sigma f of I times a, that is when I is equal to 1 to n. What that means is that you have f1 times a plus f2 times a plus f3 times a plus all the way up to f of n times a. So you can write this as a times f of 1 plus f of 2 plus f of 3 plus all the way up to f of n, right? And that's equal to a times sigma f of I as I goes from 1 to n, right? So you can take this a out. You can take this a out. So what that means is that, now these are the cool things in mathematics, really. For example, this sigma notation, that does work like magic, really. So d bar is equal to x bar minus a times sigma f of I over sigma f of I, right? And sigma f of I over sigma f of I is equal to 1. So that means that d bar is equal to x bar minus a. And so what that means is that basically x bar is equal to d bar plus a. D bar plus a, which is the same thing as so of course d bar we define that to be sigma f of I d of I over sigma f of I. So that means that x bar is equal to a plus sigma f of I d of I over sigma f of I as I goes from 1 to n, and here as I goes from 1 to n. And that is the relationship between x bar and d bar. So what that means is that now you can simply basically find all of these numbers over here, find your d of I and multiply f of I times d of I, and then calculate all of this whole business. But then at the end of the day, your calculation is much easier, and now you have this formula here. You take any a over here, any of these numbers, take an a, and then based on that you do the rest of the calculation. And then you use this formula in order to find the mean of your observations. Very interesting. And so for example, in the case of the in the case of the data that we had, over here, what we had was, let's come back to the table that we had. So over here we said that basically now the formula that I have is x bar is equal to a plus sigma f of I times d of I over sigma f of I. So this is equal to a, which is basically 47.5 plus sigma f of I d of I is equal to 435 divided by sigma f of I is equal to this was some value 512, and 12 plus 18 is equal to 30 divided by 30. And if you calculate this, you will get you will get I don't know, 435 divided by 30. Let me use a calculator. 435 divided by 30 is equal to 14.5, and 14.5 plus 47.5 is equal to 62. This is equal to 62, which is, by the way, the approximation that we found using the previous method. Not, of course, not the actual value, but the approximation value that we used, that we found, the exact approximation that we found using the previous method, which was basically multiplying f of I times x of I, f of I times x of I, and so on and so forth. So that's basically how this thing works, right? And therefore the mean of the marks obtained by the students is 62. Now the method discussed above, this method over here is called the assumed mean method. So this method over here is called, this method over here, which has basically this formula and all of the process that we talked about here, is called the assumed mean method, simply because, well, we assumed some mean over here, and then the rest of the story, of course, you already know. So that is basically that. Now the next thing that we have is some other type of material. There is actually a bunch of things here to understand, but we will get to them hopefully in no time. Okay, so now still there are a couple of things that we can do in order to further basically simplify our calculation. And one of the things that we can do is that from this table, let's say that we have this table over here. Let me basically draw some lines around this table so we know what we are talking about. First, I need to erase these, and remember that the approximation was 62, right? So now if I draw these lines around this table, and okay, so now in this table what we have is basically our x of i's are over here. So the x of i's that you have are 17.5, 32.5, 47.5, and so on and so forth. Now if you, of course you do understand that if you now basically in the calculation, I happen to take a as 47.5, right? But then based on and then I took that as a, and then we calculated basically some formula as, for example, x bar is equal to a plus sigma f of I d of I plus over sigma f of I. And we got the mean to be basically 62, which was the approximation. So we had no problem with that. So of course, in this case, now if you take your assumed mean, which is the value of any of these numbers, of course you know that the answer is going to be 62. It's not going to change, because a, it doesn't really matter what sort of value you take as a. In the algebra, it's at the end of the day, it's going to work for you. So there is no problem with that. Now, what's important here is that so basically the choice of a is not important here. Whatever the choice of a that you take from these values, basically then you put that in algebra. Basically it goes into this formula, and basically we had, let me see, we had sigma d bar, we got into this formula. So the choice of a is not important. So that is one thing. And another important thing here is that basically we got d of I as x of I minus a. So in this formula, d of I basically is x of I minus a. And as we were basically going through this table, I pointed out the fact that basically all of these d of i's is a multiple of 15, and 15 is your class size, meaning that 25 minus 10 is equal to 15, 40 minus 25 is equal to 15, 55 minus 40 is equal to 15, and so on and so forth. So that means that this d of I is actually always a multiple of your class size, right? So what that means is that you can basically you can still make this table much simpler by doing a couple of things. For example, since here we had to calculate basically f of I times d of I had to basically multiply 2, for example, by negative 30, 3 by 3, for example, by negative 15, 6 times, for example, 15, 6 times 30, and so on and so forth. So what that means is that if this number is smaller, of course this multiplication is going to be easier for me. So what I can do is that I can divide this x sub I minus a, I can divide it by the class size, meaning that if I take the class size as h, then I can divide this basically x of I minus a, I can divide it by h, and that would give me, for example, negative 30 divided by 15 would give me negative 2, this gives me negative 1, this gives me 0, this gives me 1, this gives me 2 and 3. So these numbers would be substantially basically simpler. So if I take this, if I divide x of I minus a, which is essentially my d of I, if I divide it by the class size, I can call it, for example, u of I, right? So I can write here u of I is equal to basically x of I minus a divided by h, right? I can do that, and then basically what happens is that then I can write this over here as, for example, x of I minus a, for example, all of these numbers divided by h, that would give me negative 2, negative 1, 0, 1, 2, and 3, right? And then I can calculate, each of these u of i's times the frequency. So meaning that I can write u of I or f of I times u of I over here. I can write f of I times u of I. And that gives me, for example, 2 times, for example, negative 2 is equal to negative 4. 3 times negative 1 is equal to negative 3. And 7 times 0 is equal to 0. 6 times 1 is equal to 6. 6 times 2 is equal to 12. And 6 times 3 is equal to 18. And then if I calculate sigma f of I u of I as I goes from 1 to n is going to be equal to, basically, this is 20, 30, 36, 36 minus 7 is equal to 29, I suppose. Equal to 29. And so then what I can do, so now in this situation, what I can do is that, of course, I know that u bar, I can basically take, I can take sigma f of I u of I, which is basically this thing over here. And if I divide that by sigma f of I, that would be u bar, right? Based on what we have done. So I can call this u bar and write it as sigma f of I u of I as I goes from 1 to n, for example. This you already know, divided by sigma f of I as I goes from 1 to n. And now again we can find some sort of relationship between u bar and x bar, because our goal here is to calculate x bar, of course. So we said that basically, let me erase all of these things so that we have some space to write something. So here we said that basically then basically you know that u of I is equal to, u of I was equal to basically x of I minus a divided by h. And u bar was equal to basically sigma f of I x of I divided by sigma f of I. And so I can write basically u of I f of I times x of I, right? X of I minus a divided by h. No, I'm sorry, this is u of I, right? This is u of I, and u of I is equal to this thing. So I can write this as sigma f of I times u of I, which is basically x of I minus a divided by h divided by sigma f of I. And I can take this 1 divided by h out, of course. So I can write this as 1 divided by h times basically sigma f of I times x of I. Sigma f of I times x of I divided by sigma f of I minus sigma basically f of I times a over sigma f of I, right? And so I can take this a out again, so meaning that I can simply erase this a and put it over here. So I can write it as a times this, and of course then sigma f of I by f of I is going to be 1, and sigma f of I x of I divided by sigma f of I is equal to sigma f of I x sub I by f of by sigma f of I. This is nothing but x bar, right? We said that x bar is equal to basically sigma f of I x of I divided by sigma f of I as I goes from 1 to n. So this is nothing but x bar. So that means that u bar is equal to 1 divided by h times x bar minus a, right? And so now if I multiply by h, I'll get h times u bar is equal to x bar minus a. Or I can write x bar is equal to h times u bar plus a. That means that, and of course you can write this as x bar is equal to a plus h times u bar, and u bar was this thing over here, sigma f of I u of I over sigma f of I. Sigma f of I u of I over sigma f of I as I goes from 1 to n, of course, right? So that is basically, that is how you can find the mean of those numbers, your x bar, based on basically f of I and u of I and your class size and your assumed mean and so on and so forth. Basically using all of these things that we calculated here, but now you can do it in a much simpler way. So that's basically again one problem here. And if I take this now, suppose that I use this formula. Suppose that I use this formula. Let's make a screenshot here. I don't want to rewrite this again. This recording software is not sometimes our best friend. Okay. So now let's use the formula in order to calculate the mean of all of these, basically all of these numbers again. So again we said that basically x bar is equal to a plus h times sigma f of I u of I divided by sigma f of I, right? So now let's take our assumed mean as again the same number, 47.5 for example. So then that means that x bar is equal to 47.5 plus h times, h is the class size which was 15 here, times sigma f of I u of I, which is equal to, calculated here to be 29. Sigma f of I was equal to 30, and then that gives you basically a 2 over here, and then you have 47.5 plus 29 divided by 2. So 29 divided by 2 is equal to 14.5. That's 4750 plus 14.5, and 4750 plus 14.5 is equal to 0, 1, and this is 12, 1, and that's a 62. That is equal to 62 again, the approximation that we got in this case over here. So that's again the same thing, but much simpler, much simpler. So that is that. And now this method that we discussed here, this method over here is called the step deviation method. Step deviation method. you do need to understand all of these methods and how they work in order to understand the rest of the chapter that we started, but then we got back to all of these formulas to basically to learn the basics, really. Without these basics, you cannot go anywhere, really. So now there are a couple of things here to note. The step deviation method will be convenient to apply if all the d of i's have a common factor, meaning that all of these d of i's here, if they have a common factor, which is in this case, for example, the common factor is the class size, and the mean obtained by all the three methods is the same as we saw over here. In every case we got a 62. The assumed mean method and the step deviation method are just simplified forms of the direct method, which is of course right, because the assumed mean method was the method which we developed using assuming, for example, some which by taking some number over here as the assumed mean as a, and then using that we developed a formula to calculate the mean of all of these numbers. And then the step deviation method was again based on, you could say it's based on the assumed mean method, really. And both of these methods were actually based on the direct method, which was basically nothing but f of I times x of I divided by the number of those observations, and so on and so forth. Now it says that the formula x bar is equal to a plus h times a, basically x bar is equal to this formula here, which was x bar is equal to a plus h times u bar, which was basically the step deviation method which we got in the end of the process, still holds if a and h are not as given above, but are any non-zero numbers such that any non-zero numbers, a and h, any non-zero numbers such that u of I is equal to basically x of I minus a divided by h, which is basically our definition here of u of I, basically. So, but it seems that they have to be non-zero numbers. At least h has to be a non-zero number. Now a, of course, it doesn't make any sense to take a as a zero number, because then you want to subtract it from some other numbers to make your numbers smaller. So it makes no sense to take a as 0, and you cannot take h as 0, because otherwise you would not be able to divide, really. Now, so basically the methods that we discussed here were basically a couple of methods that we will use in the future in this chapter to get ready for the chapter that we were working on. So we had the direct method. Now, I don't remember the formulas exactly, but when we get into one example, we will be able to apply all of them. We had the direct method, we had the what was the name? The assumed mean method, and there was also the step deviation method. So these are the methods that we discussed so far. Now we have, of course, a bunch of examples here. It took me days to go through this chapter. It's not more than 35 pages, but there is a whole lot of exercises here, and it's important that you do all of these exercises. But otherwise, there is a bunch of examples here. We don't have really the time to go through all of the exercises, but we will go through enough exercises to get some chances to apply these formulas in different situations. And so we will continue with that. So I'll see you in the next video with the rest of this material, and thank you.